So, welcome back. Shall we start? In the lecture plan, we have 4 hours for laser diagnostics, but I want not to dive too deep in physical chemistry to discuss with you the details of spectroscopy. So the focus of the first part here is on what reactors can we use to examine combustion chemistry. Some I have presented you already, I think 2 days ago. Today we will have a look at rapid compression machine and shock tube in detail. So the combustion chamber we have discussed already. So with these reactors, we can examine the reaction mechanisms in detail, especially selected elementary reactions. We can use other reactors we have already discussed too. So finally, we get the information we need to describe the combustion process in detail, for example, in a combustion engine. So what do we need here to predictive modeling? And the question is, okay, hydrocarbons, we know a lot, but what is with future fuels, future advanced engines? So first of all, we need, of course, a detailed understanding here of the elementary reactions and mechanism. So we have to examine the elementary reaction steps. Then we have to develop proper sub-mechanisms. Finally, comprehensive and detailed kinetic models. So therefore, we have to apply a lot of work. We can examine unimolecular decomposition recombination at high temperatures using shock tubes. We can use high pressure flow reactors. We can perform optical measurements. We can use the advanced optical light source for mass spectrometry. And altogether, we can combine the data we yield to develop the mechanism finally. The optimum setup would be a homogeneous 0D reactor where temperature and pressure are in the relevant range. It would be perfect if we have initial conditions 700K, 1 bar, and with 1 click we would yield the interesting high temperature, high pressure region within the shortest possible time. And then our examination could start. So between the initial condition and the condition we are interested in, there's of course always a gap, time gap we have to consider. The reactor should be perfect in a way that we have a homogeneous condition, so there's no disturbance by vortices, by cooling effect or whatever. And it would be nice to measure all reaction steps we are interested in. Of course, this does not exist, so we have to use different systems for different characteristic variables. So we have discussed already combustion cells, flames, flow reactors. I will say a little bit about steered reactors here today, and we'll focus on shock tubes and rapid compression machines. Advantage of these two measurement devices, so shock tube and resin compression machine. We can examine ignition delay time at given conditions, and we can perform concentration measurements of individual reactants. So we can really also look on very specific reactions, selected individual elementary reactions. So we have discussed yesterday in the Cantera part ignition delay time calculations, which we compare to also experimental data, and there I've shown you that they used a bath gas of 90% argon. So the idea here is to use bath gases, so to dilute your mixture as much as possible, so that you can really focus on specific conditions. Okay, concerning the others, I would just want to briefly introduce this jet reactor. So this was not discussed until now. The idea is to have here a perfect continuously steered reactor. So yeah, we have seen this yesterday in Cantera. So you have a homogeneous reactor with specific inlet and outlet conditions. Especially the inlet conditions you have to know in detail, and you have to know the temperature of the reactor and the pressure, and then you can use these experiments, for example, to examine your chemistry. So the idea is we have a reactant plus carrier gas, which is going through this pipe into our steered reactor. Here we have a preheating zone, but the interesting temperature is in this area here. So we have cold mixture here without any reactions hopefully taking place, and then this is heated up as fast as possible, and then it reaches our reactor, and after a given residence time it leaves the reactor again, and then we can analyze the gas flowing out of the reactor. Depending on the residence time, temperature, mixture composition, we can learn a lot about the chemistry here. So, of course, it's crucial to have a homogeneous mixture. Therefore, there's a specific setup, mostly used in literature, with 4 inlet nozzles. So 2 outflows are in this plane. One is going up, one is going down. So the idea is to create a flow field which gives you a really perfect homogeneous mixture. And this is possible in a given range, of course. So this is quite a nice setup. However, what we have to consider, this is normally not optical accessible, because it's inside an oven to heat it up to a specific temperature. So we can only examine the gas composition at the outlet. But this is sufficient for a lot of experiments, and this setup can be simulated with the continuously steered reactor model I've shown you yesterday. That means simple 0D simulations can be performed to examine the chemistry in detail. Now here I'll show you this in detail. Here we have this jet steered reactor, and here we have attached an set up time of flight mass spectroscopy. So we suck out some specific amount of gas out of the reactor, and then separate the molecules concerning their weight. So we learned a lot about on the mixture composition. Here you see the mole fractions for different reactor temperatures. And these are important information. You see we also have, so the symbols are experiments and the lines are numerical calculations. So you can perform your measurements and then use these data to optimize your reaction mechanism. This is also for liquid hydrocarbons. Of course, you need a controlled evaporator and mixer here. But nevertheless, this could be done. And here in this example, they used a gas chromatograph to analyze the mixture composition of the outflow. So now I will come to the focus of today's lecture, shock tube part 1 and RCM part 2. So I've seen the shock tubes here in Guwahati already. Maybe these are a little bit longer, but the principles are more or less the same. And of course, you have a different application here. So you have other topics in focus. Here, the focus is of course on combustion chemistry. And here we see an RCM. So I will explain this also later in detail. So a shock tube is a high temperature combustion reactor for our application. Not for your application here in Guwahati, but for our application. So we have an instantaneous change in pressure. This generates a shock wave, which we can compare to a frictionless piston. So we have a shock wave moving through our system, and this compresses our gas adiabatically. So we have hopefully a stepwise change in temperature and pressure at a given position. The advantages, it's quite simple to employ conservation equations here to describe the status before, this we know, and after the shock, which we are interested in. And it's very, very high accuracy. The change in state depends mainly on the Mach number we want to yield and the isentropic exponent. We can adjust our setup concerning the temperature and pressure range we are interested in for our ignition or reaction experiment. So, and again, this can be seen as a perfect homogeneous reactor. So again, a simple 0D calculation is sufficient to examine the reactions, the chemistry we see, also with a numerical model. So we don't have to consider about the geometry of the tube, any 2D, 3D effects. If we look at on an ideal way, so in 0D reaction is sufficient. Of course, only for a short time. And the real advantage is there is no pre-induction chemistry. So it's more or less an instantaneous change from cold mixture to hot mixture. And after this change, the chemistry will start. That's the advantage here. If we use, for example, this jet state reactor you have seen, we have a preheating zone. And of course, when we start with 300 K and have 800 K in the reactor, there is a slow change in temperature from 300 to 800. And at that time, already chemistry can take place, which may disturb our experiment. So here we talk about 700K, which is, I think, really difficult. Especially at 700K, chemistry is quite slow. So it's a problem here with this short experimental time we have. But we also can reach thousands of Kelvin, several thousands of Kelvin. So it's perfect for intermediate and high temperatures, and it can be used with some limitations also for lower temperatures. So the idea is here we have a driver section with high pressure, and we have a driven section where we also can use lower pressures, lower pressure than ambient pressure. And we have a diaphragm which is separating these two sections and can be opened in a controlled way. And after this diaphragm has opened, the high pressure gas expands into the lower pressure region. So from driver section into driven section. So we have an increase in pressure. So the pressure wave moves, or the shock wave moves to this tube, hits the end ball, is reflected, and moves back again. So we have one rise in temperature in this volume at a given time. And after the reflection, we have a second rise in pressure and temperature. So this pressure and temperature here, which we reach after the reflection of the shock wave, can be adjusted very precisely using proper pressure ratio, using proper driver gas, and so on. So we can really adjust precisely the interesting parameters here. And after this initiation, very fast, nearly instantaneous initiation of our interesting conditions. For example, here we see our initial delay time, or we see change of other concentrations, as we have the possibility to examine also optically the conditions at the test section. So what is happening here? So when we open the diaphragm, we have a shock wave which moves through our shock tube, hits the end ball, and is then reflected. We also have, of course, an expansion fan going in the other direction, which also hits then the other end ball and is reflected, then moves through our shock tube. And of course, we have this contact surface, so the area where the high pressure gas and the low pressure gas come together after opening of the diaphragm. And of course, here we have mixing and so on, a lot of disturbing processes. So, and this contact phase moves behind the shock wave through our tube. So, at that time, our experiment can start. We have reached our interesting conditions. And we have an observation time which then depends on the arrival time of either the contact surface or the expansion fan. So one of them reaches this area earlier, depending on the tube we are using. And then, of course, our volume will be interfered by other processes. So we can no longer can observe our interesting reactions here. But we have some milliseconds and so on. So for most processes, especially at high temperature, of course, this is very sufficient. So we need to know the thermodynamical data of our gases we use. But these are well tabulated, so heat capacity for constant pressure, constant volume, inner energy, enthalpy, isotopic exponent, sound velocity, Mach number, this we can find in literature. This is well known for the most gases. So how can we use this information to calculate the interesting reaction conditions? So what is the pressure and temperature after the reflected shock wave has hit our observation volume? This we are interested in because at that time the reaction starts, and then we can, for example, measure emission delay time and so on. So we have at the beginning a quiescent gas mixture, and then our shock wave moves towards this quiescent gas mixture with specific velocity. And this we can describe with a moving coordination system. So we are moving towards the shock wave. And the initial velocity here is equal to the velocity of the shock wave. So, and we are interested in, okay, this is our initial condition with known temperature, pressure, and this moves towards our shock wave, and then of course temperature and pressure will change, density will change, and so on. And of course the velocity, but this is not so much of interest. So when we look at this configurations, is it possible to determine the pressure, the density, the temperature, the velocity behind the shock wave? So we set up the general conservation equations. We cancel all negligible terms, and then we transform the equation and hopefully can calculate the conditions behind the shock wave depending on the conditions before the shock wave plus the velocity of the shock wave. So when we look at the fundamental conservation equations, this looks quite different. So we consider here only two dimensions for mass conservation, momentum conservation, and energy equation. So we have, of course, a change in time, and we have change in two dimensions. So it looks quite difficult. But when we want to simplify it, we can use several assumptions which are valid for a broad region here. So first of all, we don't have any changes perpendicular to the flow, so in this dimension, and no velocity in this direction. So these parameters we can set to 0, and we assume we don't have any change with time, which is valid for a given period too. So we can, this derivative can also set to 0. So we assume it's adiabatic, and we don't have any friction. So we don't have shear stresses, and we don't have heat flux. So these parameters can also set to 0. So we are lucky most of the variables or terms we have are deleted when we apply these assumptions on our equation system. So this is what is left over. So the momentum is conserved, and with this we can calculate velocity and pressure and energy in the second behind the shock wave. When we integrate this, okay, we see this is the outcome. Density, velocity before and after the shock, and here enthalpy and pressure before and after the shock, and with the ideal gas relation, we then can calculate the temperature. So we have density, velocity, pressure, and temperature. So these are the four quantities we are interested in. So quite simple, quite perfect. So with this, we can set up our equations here. And here we already have included the isotopic exponent and the Mach number of the Mach number of the shock and the isotopic exponent and of the driver gas. So you can see with these we see that the ratios we are interested in depends only on the composition of the mainly of the driver gas and on the initial temperature, pressure, and therefore also initial density. So, and if we increase, for example, the Mach number of our shock, we can increase the density, the pressure, and the temperature behind the shock. So here you can see the influence of this isotopic exponent. So helium 1.67, 1.4 is air, and 1.2 I'm not sure is maybe carbon dioxide. So you'll see the higher the isotopic exponent, the lower is the pressure ratio. However, we are more interested in the temperature change. So here we see if we use this helium as a driver gas, we have can reach higher temperatures at the end. So what is happening here in detail? So this is what we have before the shock, and you see here already numbers, so 4 and 1. So if you look at literature, you will often find, for example, the ratio T5 over T1. So the numbers you can find in literature I have given here. And I will explain it at which time we are looking at interesting conditions. So this is called section 4, section 1. So then the diaphragm is opened. We have our expanding shock wave, we have our shock wave, our expanding fan, we have our shock wave here, then we have our contact surface. So we then yield 2 more regions, you can see here. So, but further all I want to describe here, temperature and pressure. So when we open the diaphragm, the pressure moves through our tube, and where the shock wave was, the pressure is increased, and then we have this composition of the shock of the contact surface, and you can see it here in the temperature region. We may have an increased pressure, but here we have also a mixture of the driver gas and the driven gas, so the temperature is already quite low because it's disturbed by the mixing process and so on. And however, in the region between the position of the shock wave and the position of the contact surface, we have more or less homogeneous high temperature region. We also have this section 3 here, so between the expansion fan and the contact surface position, where we have higher pressures but lower temperatures. And we still have here 1 and 4, as we have still high pressure region and low pressure region here. Then at the end, this is what we are mainly interested in. So when we hit the end wall here, the region 4 is gone. But more of interest is we have the hit of the end wall here with our shock wave, and the reflecting wave is going back. So we have a further increase of pressure in a specific region, leading to a further increase of temperature. And this is what we are interested in normally, and this is the so-called section 5. And as I've said, this is what you normally find in literature, the ratio T5 over T1. This is why this is given as T5 over T1. So when here we have another plot for this. So we have very short time for T4, T1. Then we have some time where we have section 3, section 2. But of course, normally we are interested in section 5. And the observation time we have depends, of course, of either the contact surface, which is here. The faster one reaches our observation volume, or this expansion fan reaches our observation volume. This depends on the tube parameters we have. But until one of them reaches this area, we have some milliseconds to observe, hopefully some milliseconds to observe the interesting conditions. So in the ideal case, when everything works properly, it's frictionless, we have ideal gas behavior, so we can use this incident shock to calculate the conditions using the conservation laws and the equations of state, which we have discussed already. Another important quantity is then the Mach number of the shock, which depends on the velocity and the velocity of the shock and the temperature, gas constant, and isotopic exponent. So at the end, when we have this reflected shock, we can use our set of conservations again. And finally, T5 to P1 or T5 to T1, the interesting parameters, are a function of the Mach number and the isotropic exponent of the driven gas. I think I have often said driver gas. Of course, this is not correct, of the driven gas. So gamma 1 and the Mach number of the shock. So we have broken down the complex problem on 2 quantities, which is often helpful. So the experimental conditions behind the reflected shock wave depend on the initial state. So initial fill conditions and the shock strengths. The shock strengths depends on the Mach number and the isotropic exponent. And of course, the isotropic exponent of the driven gas depends on the investigated fuel mixture. So the Mach number here depends on the ratio of the conditions in section 4 to the sections in the driven gas. So sector 4 is the high pressure region. So the advantages here, it's quite simple to generate the interesting conditions in a broad pressure range and temperature range. We can assume that we have a homogeneous mixture with homogeneous pressure and temperature conditions instantaneously. And we can use this for several microseconds to examine the interesting quantities, avoiding pre-reaction chemistry. Of course, it has some disadvantages. We only have a few milliseconds. This is mainly the limitation to the lower temperature range. We have one experiment, so where we may perform also some laser-induced fluorescence or whatever, but we have only one shot per experiment. Then we have to refill the tube. We have to put in another diaphragm. So it takes some minutes, some time. So it's quite time consuming, and the number of the statistics you have are quite small. So of course some disadvantages. But we can use shock tube experiments to examine elementary reactions, and we can have it optical accessible. So all typical diagnostic methods can be used here. We can determine ignition delays based on different criteria, which, as we have discussed yesterday, is important. You should use the same criteria in your simulations compared to the experimental results. And we can also examine quite complex reaction system like soot formation. We can determine formation of particles in the observation volume, for example. So how does it look like? So first of all, we can use piezo pressure sensors. Even though some of you have worked here with temperature sensors. So the classical setup is using piezo pressure sensors, and then you can, for example, yield the velocity of the shock by different positions of your pressure sensors. And this is what you see here, for example, the pressure at the end wall in our section 5. We see the increase of pressure here already after the reflection wave. And then it takes some time until ignition takes place and the pressure increases further. So this can be used, for example, for a simple ignition delay time experiment. But if we have an optical window, we also can look for chemiluminescence. So CH and OH are typical radicals for hydrocarbons, hydrogen. So we can measure the emission in the range of 308 nanometers and or 430 nanometers, which are the typical bands of these two radicals of interest. And well, we see an increase, and this can be used, as we have discussed already yesterday, to determine an ignition delay time 2. And this normally not gives better ignition delay time, but it gives us a delay time which we can better compare to our numerical results. We can use other optical techniques. So we can have a laser light source here. When we have windows here, we can measure, for example, absorption based on Lambert-Beer law. So when we have a laser with a well-known wavelengths, and we know there's absorption from a specific molecule in this wavelengths, we can use this laser, measure the absorption, and then we can, as we know the distance here, we can calculate the concentration, the amount of interesting molecules in this area. So this is a function, the ratio of the light intensity is a function of mixture composition, but also of course pressure and temperature. We can use also Schlieren measurements. I have to check if this video is running here. So we look now in section 5, and hopefully see shock is coming from the left. Sorry, it has worked on my computer. So what we would have seen is shock coming in from the left, going back, and then after a given time ignition takes place. We can use a gas chromatograph to suck out some gas and examine the mixture composition. We have after ignition, for example, quite simple setup, and if we perform this at specific times after the ignition, of course we can get some additional information and some final simple experiment here. So we can also examine specific elementary reactions. We have, of course, no single shot experiment, so we get one signal per experiment. But we can use this to examine specific reactions, which gives us some limited information, but this can be used, for example, together with numerical work to examine reactions in detail. Here in this example, they have used butyl hydroperoxide and methyl formate in a bath gas argon, and then we have this incoming and reflected shock heating up our system. So these two molecules are separated. So here we produce instantaneously OH, more or less. Here we produce CH3. So, and for example, here we can see the amount of OH. So after the shock, here we have the decomposition of this molecule. OH increases and then it decreases, and the decrease here depends on the reaction of the OH molecule with methyl formate or CH3. So we can examine this one elementary reaction here in detail. And when we know something about possible second reactions here, where we can use, for example, numerical simulations, we can see here the sensitivity of OH concerning specific reaction as a function of time. And what we then see is that this reaction, CH3 plus OH, giving CH2 plus water, is the main interesting reaction. So OH is very sensitive, the consumption of OH is very sensitive concerning this equation here. So we cannot use this experiment only to get information about the ignition delay time, but also we get further details about specific reactions here. But okay, back to ignition delay time. This plot we have seen, or a similar plot we have seen yesterday. So the ignition delay time of N-heptane at specific conditions. Here, ignition delay time as function of temperature at 2 high pressure conditions. And we see again our negative temperature coefficient we have discussed already yesterday. So each triangle represents one or set of experiments at specific temperature and pressure. And so this is what we have done yesterday. The simulations here show sufficient agreement. So a shock tube, of course, then can easily be used to determine ignition delay times in an interesting temperature range. But that's the past. Actually, this setup is mainly used to examine modern renewable fuels. So alcohols are of interest, dimethylfurane, and so on. So different fuels are of interest today, and the idea is actually we optimize our combustion engine based on the fuel we have. So we have diesel, we have gasoline with specific composition, and so the combustion engine is optimized here concerning this the quantities of our fuel. But if we can design our fuel, then we can optimize the combustion engine for perfect efficiency, and then design our fuel for the conditions we need with this combustion engine. That's the idea. So to change the optimization way. And so first of all, then we need to know more about the possible design fuels we have. So we performed similar experiments which were done with the classical hydrocarbons. So here this dimethylfurane in the ignition delay time are examined at specific conditions. So we use again ignition delay time and can compare this. And first of all, it's very important to realize, of course, different molecules gives us quite different ignition delay times at higher pressures and at lower pressures. So this information then can be used to examine the difference further, and this is what we see here, that there are regions where we always observe differences between the molecules. So, and then this data we need finally to optimize our design fuel, which may be a mixture of these or other components. What do you mean with explain?
actually, what is the physics behind that? I do not understand it.
Pardon?
What is the why it is being formed there? That zone, expansion band zone, why it is forming there?
So that's energy conservation. Of course, you have a shock in this way, so because there is a compression, sudden compression, we have an expansion in the other direction. So here's high pressure region, here's low pressure region. So the shock due to this high pressure meets low pressure, moves in one direction, and of course it expands then in the other direction. So pressure is increasing here and decreasing here. But this is normally not of interest. So this is not an observation volume. Therefore, I'm not aware that if there are is there any work where they examined the influence of the expansion fan on the section 4. Because finally what is of interest is at which time the expansion fan reached our section 5. This is the quantity we are normally interested in. So, as you may have heard, I'm not an expert here because I haven't bothered about it until now.
And the pressure maintained in the test section, in the pressure maintained in the test section, section 5 I think. So is it, what is the range of pressure that can be maintained there? Like in the real engine combustion condition, the pressure is varying like up to 50 bar, 45 bar.
Yeah.
So here somewhere I have seen the pressure is like 1 bar to 100.
Yeah, that's the initial condition. So, and we can go below 1 bar, but we can. This mainly depend on the strength of your piston or the tube you use. So 100 bar is no problem here.
Okay, so by increasing the length, what you have shown, so that is the existing soft tube in the PT. So it is having a driven length of 11 meter.
Yeah.
So by increasing length, how fold the timing is increased?
Yeah, if we increase the length, we increase the observation time.
Yes. So
Yeah.
how fold it is increasing? What is the maximum amount of time? So there is a number.
I have no guess here.
Reaction time.
No.
Time before the contact surface or the expansion can meet the surface, the reflected surface.
Yeah, so we will see it after the lunch break. We always have a real shock. And this, what I discussed now with you, was a perfect shock. Of course, we also have disturbances due to the shock, which influences the delay, the time. So it wouldn't help to have an infinitive long shock tube here, and then to have an infinitive long observation time. This won't work. So there are some limitations, but you have quite impressive long shock tubes in combustion experiments. So they have some milliseconds here, but I don't know the upper limit here. Sorry.
So can it replace RCF?
Hmm?
Can it replace RCF?
Yeah, that was the fear of the RCM guys. So as I've shown, up down to 700 Kelvin, we may use it. I think we then have a region where both can be used. One big advantage of RCM is it's fast. So we have a high repetition rate. That's a big advantage. So we will see it later today So both have their advantages and disadvantages, and it depends on your application too.
But here the amount of gas required is in some 200 something liters. So at a single go you have to consume a lot of gases, and helium is anyway very costly.
Yeah, okay. You mean the cost per experiment
Yes.
are higher for a shock tube? Yeah, yeah. This is also okay. Scientists normally don't look at money, but this is of course of interest too. Yeah.
Yeah, we try here with nitrogen and helium also, but maximum time we go with nitrogen.
Yeah, helium is
Exactly.
unbelievable expensive in our days. Yeah.
And with this driver pressure of hardly 25 bar, we use go for maximum of 25 bar. And with that, we can achieve a shock of around strength of 2.5 to 3 Mach.
Mm-hmm.
So by this XT plot, so we calculate the timing is around 1.2 millisecond around that one. So this reaction time. That's why we have not tried that concept here by putting the reaction mixture at the test gas.
Because it's too short, or well,
No, means that putting this reaction, making the mixture composition perfectly, and again trying this one. So that part we have not tried it.
no. Yeah. So we have just talked now about the length of the pipe,
Yes.
but also you have to consider the diameter,
Yeah.
because we always have a real shock, and the combustion shock tubes often are very big in diameter, so it's also expensive then.
Here we mostly go for achieving this planar shock waves. So that's why we have kept 7 meter of long, and that is sufficient for us. 7 meter, 2 meter of driver length and 5 meter of drivel length. So that is giving us a planar shock wave. So we have not increased that one to more.
Yeah, then of course if you don't have further needs, you don't have to
Yeah. That's
invest here more. Yeah.
And when we are in the mixture, when we are mixing the reactant, test gas, so how the homogeneity is maintained? The mixture is not homogeneous when you are putting mixture there.
before it is mixed and the mixture is placed as a test section. Right.
So when you
After mixture time.
Yes.
fill in your mixture, normally you wait some time, and then you have hopefully increased homogeneous mixture. But that's, for example, the disadvantage when you use ammonia. Ammonia then stick to the surfaces. So, of course, there are some effects which have to be considered. So until now, we have talked only about the perfect world, not the real world.
Actually, in PTB, like when you are using ethanol and and butanol, generally, what way you are doing that?
Yes.
Generally, what way you are doing? We are pre-mixing it and putting it in the driver section, or it's as it is. We are just supplying the gas inside it. Right?
Yeah, okay. And butanol is a liquid,
Yes.
so of course we have a mixing device in advance, and then we normally have already heated above the boiling point conditions before the shock.
So that means it is being preconditioned.
Yeah, the precondition must be adjusted here, of course.
Sir, which gas we use as a driver gas here?
Yeah, normally it's often it's helium, but as we have heard, it's also expensive. So you can use nitrogen, you can use carbon dioxide.
And sir, here for shock, sir, diaphragm is moving, or we just remove the diaphragm?
Pardon?
Sir, here for moving for shock, we have to remove the diaphragm, or diaphragm is moving?
You have to remove it.
We have to.
Yes.
Yeah, it's normally it breaks at a given pressure.
Okay, and both gases will mix together. No? Driver gas and driven gas both mix. No?
They mix.
Mix together for shock.
Yeah, that's this region here.
Yeah, both gases mix together.
No. So before the shock, we have a clear separation.
Okay.
And then this diaphragm is opening. And then, of course, we have a mixing region. But this is all not of interest normally. The only interesting factor is how long it takes the contact surface to reach our observation volume. So, if there are no further questions, enjoy your lunch and we'll meet again at 2:30. Thank you.